Okay, let's begin coordination polymerization part. So at the beginning of coordination polymerization, we'll review some of the parts that we have learned at the beginning of this semester on the stereoisomerism. So as you recall, stereoisomerism basically means the different spatial arrangement or configuration of the substituents. So let's see an example. If you consider mono-substituted ethylenes, basically alpha olefin, okay? If you synthesize polymer based on this vinyl monomer, you can generate chiral center as shown here. Okay? So depending on the position of this R group, we could generate isotactic, syndiotactic, or atactic polymers based on these structures, based on the three-dimensional arrangement of these R groups. Okay, so in regard to this, we have learned about the resulting polymers of these dienes, right? You might remember this 1,3-butadiene or the 2-substituted 1,3-butadiene, okay, such as isopurine or chloropurine. So, for example, if you consider the synthesis of 1,3-butadiene, basically forming polybutadiene, 1,2 or 3,4 polymerization in this 1,3-butadiene basically generates the same polymers, right? Because the 1,3-butadiene is basically symmetric molecule. Okay, the resulting polymers are same. Okay, and also depending on the position, three-dimensional position of this R group, we could generate isotactic, syndiotactic, or atactic configurations. But in the case of isoprene, which is not symmetric, okay, 1,3 polymerization and 3,4 basically generates different structures. Okay. And if you do the 1,4 polymerization based on these dienes, you can generate either cis and or trans configurations. And if you compare these cis and trans structures, generally trans structures are more stiff. Okay, basically it has higher crystallinity compared to relatively flexible cis structures. So as an example, if you check the properties of stereoregular polymers such as for polypropylene, so if you compare the physical properties of this polypropylene for isotactic, syndiotactic, and atactic polymers, atactic ones are quite useless in terms of industry, but isotactic polymers, isotactic polypropylene with high melting point and also really high mechanical and thermal resistance, they are generally applied for a variety of applications. And compared to these isotactic polymers, syndiotactic ones are less common. It's less common to synthesize syndiotactic ones. And regarding these cis and trans configuration and their properties, this is not really given here. Let me show you an example. Let me just write a table. So if you compare 1,4 polybutadiene, okay, this one. So not this one is isoprene, but if you generate polybutadiene from this 1,3-butadiene by 1,4 polymerization method, you can generate cis and trans form, right? One for polybutadiene and also for 1,4 polyisoprene. This one and this one. Okay, if you compare these two for cis and trans configuration, cis and trans configuration, if you compare the Tg and Tm, you can see clear difference between cis and trans form. For example, for 1,4 polybutadiene, cis 1,4 polybutadiene have Tg, this is degree C, Tg of minus 102 degrees. On the other hand, trans 1,4 polybutadiene is minus 58, much higher. Similarly, for melting point, this one is about 1 degree C, but this one is about 100 degrees C. Sorry, 141, much higher. And this clearly shows that trans 1,4 polybutadiene is much higher crystallinity compared to cis. Okay. Similarly, 1,4 polyisoprene also have similar trend in terms of Tg. Cis one is minus 73 and trans is minus 58. For melting temperature, it's 28 and 74, also much higher values for trans configurations. Okay. Then what exactly affect these stereo regulations if you do the polymerization reaction? So there's no, so this is, so here you should put forces of stereo regulations in alkene polymerizations. So let's read. Stereo regularity is determined by relative rate at which an incoming monomer molecule is added with the same configuration as the preceding monomer compared to the rate of addition with the opposite configuration. So basically, if a certain polymers have higher portion of, let's say, isotactic portion, isotactic configuration, which means that the monomer, when the monomer is added to the growing chain, it is added in the regular manner, right? And that regular adding is much faster than the addition of the monomer in the opposite direction. Okay, and that relative rate in a regular manner is dependent upon the many different factors. In the case of free radical polymerization, it depends on temperature because active end is basically free radical. Okay, there is no counter ion, etc. Right? For in the such as like in ionic polymerization. But on the other hand, for ionic polymerization, at which there is a counter ion attached to the chain end, right? So it's kind of coordinated. There is some steric, also electrostatic interactions between the chain end, the active site end, and the counter ion. Then the stereo regularity depends also on the coordinated complex or also the solvent. So let's see some examples. So for example, for free radical polymerization, let's say that you are making the PVC using this method. Then by changing the polymerization temperature, you can clearly see that as you decrease the temperature, you basically get more syndiotactic configuration compared to a tactic one. Similarly, if you do the radical polymerization for making PMMA, as you decrease the temperature, you can generate more higher tacticity. Okay. The reason why is this when you remember, if you consider the structure, chemical structure of PMMA, this MMA substituent is very large, right? It's kind of bulky. So because of static and also electrostatic repulsions, it's kind of relatively easy to make synthettic polymers compared to, let's say, like PVC. The fraction of the synthettic portion is larger, right? Like 0.87, something like that. Even at high temperature, it's like 0.64. How about ionic polymerization? This is factors affecting stereoregularity of polymers in ionic polymerization. Similar to the free radical polymerization, temperature also is a factor which affects the stereoregularity. So at lower temperature, we basically get the higher tacticity. There's also effect of a counter-ion. So we have polymer chains with some, let's say, some ion, like positive or negative ions. Let's say that we have negative ions here. And if there are three different counter-ions, lithium plus ion, sodium, or potassium. And you know, all these three, lithium, sodium, and potassium, are alkali metal with the same charges, +1, but the sizes are different, right? Lithium is the smallest one, larger, and the largest one is the potassium, okay? Because of the size, okay, and with the same charges, +1, which means that this lithium has the largest charge density, right? Charge density means the charge per volume, okay, because it has the smallest volume. Because of the largest charge density, this lithium plus ion is more closely attached to these negative ions on the polymer chains. Okay, because of this close distance between the polymer chains and the counter-ion, the lithium as a counter-ion tends to form more isotactic polymers. Another effect is effect of solvent. So if you use polar solvent in doing polymer synthesis, polar solvent tends to dissociate these two ion pairs, right? Polymer chains and the counter ions, right? Because of the interactions between these ions and the solvent, right? That the distance between these two ions, the distance becomes larger, right? Then the tacticity it gets kind of lower. So compared to isotactic, synthettic polymers tends to be formed more, but in the case of non-polar solvent, it just affords tighter ion pair. These interactions are tighter, and which means that the distance between these two ions becomes smaller. Then we can generate more isotactic polymers. In regard to this coordination polymerization, we have to remember Ziegler-Natta catalyst. So this Ziegler-Natta catalyst was developed back in 1953 and 4. What these two people developed is the new catalyst to synthesize polymers. And before the development of this new catalyst, when people did the synthesis of, let's say, polyethylene, they could only get very low crystallinity polyethylene. Before these catalysts, the people could not really get high crystallinity polyethylene, which is much more useful, right, compared to the low crystallinity polyethylene. So Ziegler catalysts generally include metal alkyl or halide of group 1,3 metal and transition metal salts as a co-catalyst. And by using this catalyst, he could synthesize the polyethylene at these reaction conditions, and the resulting polyethylene was really highly crystalline and also high density, which means that the tacticity was really high. Like the portion of isotactic or syndiotactic polyethylene was much higher than before. Similarly, NATA used the similar catalyst to synthesize polymers based on alpha olefin, and he could also find that that specific catalyst could make a much stereoregular, high degree of stereoregular polymers. So let's see. So let's just see briefly the general feature of this Ziegler-Natta or coordination catalyst. So generally, in heterogeneous, as a heterogeneous catalyst, Ziegler-Natta catalyst means these two catalysts. This is the catalyst, titanium chloride, and this aluminum triethyl aluminum is the cold catalyst, which is used to get in combination with this catalyst. And by using these catalysts, they could generate like really high stereoregularity of polypropylene. And for homogeneous catalysts, metallocene are commonly used. And let's see what metallocenes are. So metallocene catalyst looks like this. Basically, there is at the center of the catalyst there is a metal such as iron, titanium, or vanadium, and these ferrocene molecules. Ferrocene, this molecule is called ferrocene. Ferrocene molecules are coordinated to this metal. So generally contains two ferrocenes. Okay, two cyclopentadiene is ferrocene, anions bound to metal center. Okay. And these catalysts are homogeneous catalysts, which basically act similar to the Ziegler-Natta catalyst. Okay. So let's briefly see how these kind of catalysts with these kind of chemical structures can generate highly stereoregular polymers. So there are many different mechanisms, but below shows the representative mechanism of Ziegler-Natta catalyst. So here shows the catalyst. Okay, there is titanium at the center, and titanium has 6 coordination part. Okay, and 4 of them are chlorine, and there is another ligand L here, and one of the coordination site is empty. Okay, and then it reacts with the co-catalyst, this one. Okay, and this R group is attached to heat. Basically replaced by this, replaces this chlorine, so takes one of these coordination site. Okay, and there is one coordination site is empty. Okay, this one is empty, and based on this active catalyst, if you use this alpha olefin as a monomer, it is attached to this empty site in this manner. Okay, and the position of these ligands are kind of rearranged in this way. Okay, so these monomer molecules are moved to this upward side, basically generating empty site again. Okay, and this empty site is also again attached by this alpha olefin monomer in this way, and this monomer is also rearranged in the same way as this monomer is rearranged in this way, similarly. Okay, so this kind of rearrangement is basically occurring in pretty much the same manner, same in 3-dimensional, same configuration. Okay, so by doing this kind of rearrangement again and again to this empty site of this catalyst, you can generate highly stereoregular, like high degree of isotactic or syndiotactic polymers. Okay, so I mean, we don't really need to worry about the detailed mechanism. We don't really need to memorize it. Just take a brief, like understanding how these kind of catalysts are used and for what purpose. Okay, that's the more important aspect of this coordination polymerization part. Okay, so let's start the part titled Types of Polymerization. Actually, this is the last part of the lecture. So there are mainly 4 different types of polymerization. 2 of them are considered homogeneous, and the other 2 are considered heterogeneous. Okay? And all these 4 types of polymerizations are based on free radical polymerization. So basically, the overall polymerization method is free radical, and I also explain again, but the polymerization mechanisms are same as free radical polymerization for most of these types of polymerization method. So let's see one by one. So the first polymerization method in homogeneous polymerization is called bulk or mass polymerization. Okay? So in here, we only use monomer and initiator. And generally, monomers are in liquid phase, and also initiators are liquid, and these two are miscible with each other. Initiator are soluble in monomer. Okay, so we simply just mix them together. We just put monomers and we add small amount of initiator. Okay, and you may just do the reaction. It's kind of quite simple, right? And as you recall from free radical polymerization kinetics, the propagation rate, the polymerization rate, is proportional to the monomer concentration and the root of the initiator concentration, and the number average degree of polymerization is proportional to the monomer concentration, and inversely proportional to the root of initiator concentration. So by by changing this monomer or initiator concentration, you can modulate the propagation or the polymerization rate and also the molecular weight of the resulting polymers. So if you consider the advantages and disadvantages of bulk polymerization, since we only use monomer and initiator, basically there is no contamination. Okay, so we are basically using chemically pure monomers and initiators, so the product are really high purity. But the problem of this bulk polymerization, disadvantages include it's difficult to control because of the free radical reactions that we have learned before. Okay, we learned about the auto acceleration, right? Auto acceleration at high conversion, and since we are using basically high concentration of monomers, we are basically using only monomers and initiator, right? So it's really high concentration. So at high conversion, because termination rate decreases with the higher viscosity, we can experience this auto acceleration or gel effect, right? And we learned that it could be quite dangerous, right? Explosion can occur. Okay? And also at high conversion, because of this high concentration, the propagation rate and the kinetic chain length also increases, which means that it is we basically generate a relatively broad molecular weight distribution. Okay? Basically, broad molecular weight distribution means that the uniformity of the polymer properties are not really good, right? So we want to make basically relatively narrow molecular weight distribution, right? But when you make the polymer using bulk polymerization method, it's not really easy. And similarly to the number one, the auto acceleration, since the propagation is exothermic, heat removal is also a problem. I already mentioned that explosion could happen, right? So if you want to make polymers using bulk polymerization, what you can do is you just keep it to low conversion, because high conversion could make some problems, right? Okay. Just keep it at low conversion and just stop the reaction and just do it again. Okay. Similarly, you can just do the reaction at low conversion and stop it, and you can just make it as a film. You just pour those the resulting polymers into some kind of mold and just make a sheet, like a paper type polymers. So these bulk polymerizations are generally used in generating, such as polyethylene or polystyrene. The second method is called solution polymerization. Okay. So unlike the bulk polymerization, at which monomer and initiators are only used, here, in addition to monomer and initiator, solvents are used. Okay. So the resulting polymers, after finishing the polymerization reaction, polymers also remain soluble. Since we use solvent, and solvent is in large amount compared to monomer and initiator, solvent can act as a diluent, so we don't really need to worry about the exothermic reaction. And also solvent reduces viscosity. We don't really need to worry about gel effect even at high conversion. So it's basically same way. Thermal control is easy. But the problem is, since we use solvent, chain transfer reaction can occur to solvent, right? And we learned that if chain transfer occurs frequently, then it's not easy to make high molecular weight or long chain polymers, right? And another problem is, after finishing the polymerization reaction, we need to remove solvent, right? We only want resulting polymers, right? Then this could be a problem, and also if we use kind of environmentally toxic solvent, then it could be an environmental problem. Okay, and solution polymerizations are used for small amount of specialized polymers such as SPS, PVA, PMB. Okay. Anyhow, both of these bulk and solution polymerization, we can describe the overall kinetics by free radical polymerization that we have learned before, right? Such as like RP and this kinetic chain length as shown here. Okay, same general kinetics. Okay, so these two, bulk and solution polymerizations, are considered homogeneous, right? All the species, monomer, initiator, or solvent, are in the same phase, right? Generally in liquid phase. The other two methods are considered heterogeneous polymerization. There are two different kinds. One of them is called suspension polymerization. The other is called immersion polymerization. In suspension polymerization, we basically have initiator, monomer, and water. So basically we do the polymerization reaction inside of water in aqueous phase. And generally monomers are non-polar materials compared to water, right? Water is really polar media. Okay? So monomer is suspended as droplet, such as like oil droplet inside the water. you can just imagine that you just put some oils inside of water and you just agitate it with like glass bead. Then you can generate small oil droplet inside of more water, right? So in similar way, monomers are suspended as droplet, and droplet sizes are like relatively large, right? 10 micron to 1 centimeter in diameter. Okay, so we can maintain this suspension by agitation. Without agitation, those droplets will be combined with each other, right? Because monomer and water are insoluble with each other. Okay, and in suspension polymerization, we add some amount of water insoluble inorganic stabilizers, which helps to stabilize the formation and the continuous maintenance of these suspensions. And since initiator, monomer, and also polymers are insoluble in water, so basically there is no picture here, but let's say that we have water and we have droplets. Okay, so these are monomers, and initiator, since initiator is also insoluble in water, initiator and monomers are together inside of these droplets. Okay, and these droplets are just directly converted to polymers with similar sizes, right? Basically, polymerization occurs inside of this monomer droplet or monomer, these small droplets in size of tens of microns to like 1,000 micron, right? Okay, it's very simple, right? So it's widely used in even industrial scale. Okay. So if you check the general feature of this suspension polymerization, because we are using water as a reaction medium, basically we can have low viscosity and easy heat removal. But the problem is, after finishing the polymerization reaction, we need to remove these resulting polymers from water, right? We need to separate and purify polymers. Okay. And kinetics are basically same as theoretical polymerization. The last polymerization method is called emergent polymerization. So there are some similarities between suspension and emergent polymerization. So here in emergent polymerization, we also have monomer, initiator, and emulsifier, or called surfactant. And also we use water as a reaction medium. But the difference is, in suspension polymerization, monomer and initiator were water insoluble, right? So remember here, okay, initiator and monomers are insoluble in water. Okay, that's why this polymerization reaction occur inside of these monomer beads. But here in emergent polymerization, monomers are slightly water soluble, and initiator is water soluble. That's the main difference between suspension and emergent polymerization. Okay. The usage is, you can just read it, just not that important here. Okay. It's generally used for some specific polymers. Okay. Advantages include so the details information about this emergent polymerization is not that important. So I'm going to just skip this part first, and let's see how this emergent polymerization occur by looking at the pictures here. Okay. So as I just mentioned, in emergent polymerization, there are monomer, which is slightly water soluble, initiator, which is soluble in water, emulsifier or surfactant, and water. Okay. We all know what emulsifier or surfactants are, right? Surfactants are basically long chains with the head group, head and tail. And head groups are polar and tail groups are non-polar, right? So inside of this water, these surfactants basically form this kind of micelle structure. Okay, this is micelle, and inside of this micelle, monomer molecules tend to form because monomers are slightly water soluble but mainly non-polar, right? Okay, so there are monomer molecules inside of here, and monomer molecules are surrounded by these surfactant molecules, right? Basically, they form micelles. Okay, and initiator, which is water soluble, initiator is around here. Initiator, I mean, while maintaining its position inside of this water medium, sometimes it could go into this micelle. Then they can just start the reaction, right? They can just start the reaction inside of this micelle, and it can generate the polymers based on the reaction between active centers and the monomers. Okay, so basically reactions are occurring inside of this micelle. As I written here, polymerization mainly occurs inside of these micelles because of high monomer concentration in it. Okay, because monomers are mainly non-polar. Okay, although if they are a little bit water soluble. And here they have, since this size is relatively small, it has high surface to volume ratio. Okay, and mainly these parts are non-polar, but water soluble initiator can go in to start the reaction. Okay, so if you can control the amount of surfactants, you can also the amount of monomers, you can easily control the molecular weight of the resulting polymers. Okay, so the overall reaction mechanisms are shown here, right? First, formation of this nucleus surrounded by the surfactants, and the growth, and then monomer finishing. Okay, it's quite simple. So let's go back. So the advantages of these emergent polymerization include similar, right? Thermal and viscous problems are minimized because we are using water as the reaction medium. Okay, but the kinetics are different. So I'm not going to go into the details about this derivation of these kinetic equations, but the resulting kinetics, the kinetic chain lengths, the dependence on the monomer concentration or the propagation rate is different from the other types of polymerization method. I mean, you don't really need to memorize this, but anyhow, there are some differences because the emergent polymerization uses the surfactant, so we need to consider that. Okay. And emergent polymerization allows molecular weight to be increased without decreasing RP, right? Because the reaction occurs inside the micelle, right? If you control that or the concentration, then you don't really need to worry about the change of polymerization rate. So I'm going to just skip this part, and I already mentioned this, right? Differences between immersion and suspension polymerization include: in suspension polymerization, initiators are not soluble in water, but in immersion polymerization, initiators are water soluble. And in suspension polymerization, the size of the suspension is relatively large, right? From 10 micron to like up to centimeter size. But in immersion polymerization, the sizes are much small, right? In nanometer range. It is just determined by the size of the micelles, right? And in immersion polymerization, we use emulsifier or the surfactants, right? But in suspension polymerization, we are not using these surfactants. It's almost done. This is the same one, okay? So these surfactant molecules, as you all know, have these kind of chemical structures, right? Hydrophobic long chain and hydrophilic head, right? And these hydrophobic chains generally have 10 to 20 carbons. Okay, and typically dodecyl sulfate with 12 carbons are generally used. And these hydrophilic parts are water soluble, but these hydrophobic parts, which are not water soluble, they form micelle structures. Okay. The other parts, I'm going to just skip the other parts. It's not that important. So this is pretty much it for the types of polymerization. So there are 4 different types, 2 of them homogeneous, 2 other heterogeneous. You can just briefly, just qualitatively understand the major features of each polymerization type, and also the advantage and disadvantage, some comparison between them. Okay, that will be enough for the understanding of different types of polymerization.